this computer. And the importance of this recording business, I think, came up in my morning class today at 9:30. I would get a pop-up saying my internet connection is unstable. And then I looked over in the chat later on and I saw that about that time they said my voice was breaking up. Okay. And that's going to happen a lot, I think, over the next, what, we got 3.5 more weeks. Into week 2 here, 3.5 more weeks till the end of the semester. The reason I'm recording is so you can always come back and look at it later. If my voice is breaking up and it's not getting fixed and it's so distracting that you're really getting nothing out of sitting in the Zoom meeting, feel free to leave and watch the video later. I can see people are watching the videos. It's on my YouTube channel, so I get to see the views. And so I know if people are looking at it, and I see people are. So if you're not here, that's fine. You just have to view it asynchronously. And of course, the proof of the pudding is that you're doing the worksheets, the tutorials, and that those are being turned in on time. There is going to be a homework coming out on chapter 3 next week. I may get it out today. We'll see. I want to keep it around 3 problems. I've pretty much decided on 2 of the 3, and I'm searching around for that perfect 3rd problem on this material. Okay, so I do want to review. We're in the middle of what I think I described on Wednesday as one of the most important problems in chapter 3, and that is we've talked about having this eigenvalue system because Schrodinger's equation is an eigenvalue problem. Once you go to the time independent form. And so if you remember last time, we had this generic operator in an eigenvalue fashion, and we were given 2 constraints, I guess is how I'd see these things that are circled, okay, and a basis that we were working in. And remember, the basis was just I would call it analogous to an X and Y coordinate system. One of them was that, and we called that thing E1. Okay, so just 1 in the first thing and 0 in the other. And you notice that it is normalized, right? And the other was E2. And that was just equal to the Y unit vector, I guess. So I can see this is an X and a Y unit vector, basically. It's a 2-state system. And I don't know why we went forward here, but the question, I guess, is with these constraints, how do you construct the matrix, which is going to represent the operator? And by the way, this was just an algebraic expression. I think, Peyton, you asked a question the other day, could this be a math function? And the answer is yes. And you could have a 2x2 operator that is a matrix, represented as a matrix. Okay. Let's see, Jake, are you saying something there? I'm talking. Got a question?
I sent a message in the chat.
Okay, when I'm working, I can't see the chat, so you just got to kind of chime up. What's the question?
Is there a tutorial to go with today's lecture?
Yes, there is. I posted it last night, and it'll be due next Wednesday. So yes, in fact, the problem we started on Wednesday that we're going to finish up today is that tutorial. It's just a slightly different problem. It's similar, so you should be able to follow through what we did on Wednesday and what we're going to finish up today, and that is the tutorial. So yeah, it's called Using Dirac Notation is the name of it, Using Dirac Notation Tutorial. And it basically goes through exactly the steps that I'm reviewing today and continuing on with the problem. And that's it. Good to go? All right, so anyway, you got to construct the matrix that is the operator that is going to be, you could from that get an observable as an expectation value if you wanted to. That's not the direction we're going to. We first are going to get the eigenvalues, which could be the expectation values of that particular operator. Anyway, so you have to do it. And remember what we said was that's how you get the individual elements. So if you want to get 1, 1 here, you slap in E1 right here, and you slap in E1 right there, and you put in the operator T right here. And you can see when T operates on E1 right here, you get an I. And let's see, and then if I get E1 right there, well, that creates the thing I need right there. So I guess this component right here should be I. And let's see if I got that right. No, I didn't. What did I do wrong? Let's see. Oh, that's E2. That's why, because
Yeah.
it's E2, and I multiply, so that becomes 0. Yeah, I'm not reading correctly this morning. I get my glasses on. So that became 0, and we did all of those. All right, and that was the result. That was my Hermitian operator. Turns out, notice if I interpose or transpose those two things and take the complex conjugate, I get back my original matrix. And we said we wanted to solve for the eigenvalue. These are eigenvalue problems. And the way to do that is to multiply the eigenvalue by the identity matrix and then subtract it from the original matrix, the operator matrix, and then realize we're not letting the eigenvectors be 0. That would be trivial. So that must mean the subtraction between the operator matrix and the eigenvalue multiplied by the identity matrix has to be 0. And if a matrix is 0, that means its determinant is 0. And that gave us a polynomial. In this case, since it was 2 by 2, it was quadratic. Not a hard quadratic, but the eigenvalues in this particular problem are +1 and -1. Okay, once we had the eigenvalues, we plugged them back into the original eigenvalue matrix equation, and we found out the relationship between the two elements A1 and A2 of the eigenvalues for each of the two cases, for the +1 eigenvalue case and for the -1 eigenvalue case. And I just slapped them on there in order to give them a name. Okay. And it looks like you get two equations when you do the matrix multiplication, but they both yield the same answer, how A2 relates to A1. So that's all you can say about the eigenvector for the eigenvalue +1 case. And similarly, this is all you can say about the eigenvector for the eigenvalue -1 case. And so the question might be, well, how do I get A1s here out of this? How do I get the answer? What do I need to finalize my answer up? And the answer is you normalize the eigenvectors. Just like back in chapter 1, when we proposed a solution to the infinite, actually chapter 2, to the infinite square well, we said the solution was like a sine or a cosine. We used sine because we were asymmetric. We had a times the sine of basically a kx. And what was a? Well, you normalized it to find a. Same thing here. And when we do that, we find that the normalization constant for both of these is 1 over square root of 2. And so that must be what I bring out. That's really 1 times 1 over the square root of 2. I over times 1 over the square root of 2. I factored out the normalization constant, which is often what we do. In any event, you can see these are my two eigenvectors. I can write them in terms of my original basis like this, because 1, 0 is what E1 was, and 0, 1 gets me the I, which is what the second one is. So those are my two eigenvectors written in terms of my original basis that I started the problem with. And I checked everything, made sure that that the eigenvalues they did work. Okay, when I got the eigenvector and the eigenvalues, sure enough, if I take the matrix operator, I multiply by one of the eigenvectors, I get the eigenvalue times that same eigenvector back, which is what I have to get, right? I have to get the t when it operates on one of my eigenvalues is equal to the eigenvalue associated with that eigenvector times the eigenvector. That's an alpha. It's just a lousy looking alpha. You got to get that, okay? And I did want to check to make sure my eigenvectors were orthogonal, okay? So when I multiplied them together, sure enough, the inner product of the two was 0. All right, and so we did talk about, well, what if it was a Hamiltonian? And that isn't what the worksheet does. But what we did talk about on Wednesday, just before we closed, is okay, what basis was this all done in? And the answer, of course, was it was done in that original basis set that looks like unit vectors I and j, 1, 0, 0, 1. And we made the point that, whenever you specify an operator, then it is tied to a basis. And sometimes that might not be the best basis to be working a problem in. You might want to change to a different basis. And I made this comparison, that's the position operator in a position basis. This is the momentum operator in a position basis. Well, what if you went the other way? It turns out, and I'm not proving it, that in momentum space, the position operator looks like that. And the momentum operator, of course, is just P, just like X is in momentum space. And so we made some comments about how there really is this state vector, and the wave functions that we've talked about are just that state vector expressed in a particular basis, which then I think begs the question, how do you change basis? What is the process mathematically in linear algebra by which you go from the original basis we were in, that was the unit vector, the 1001 basis, and how do we change to something new, okay, to a different basis? And there was the Dirac notation tutorial, the one we did before the break. It told you how to transpose from one basis to another vectors, okay? And if you remember right, the bottom line is you took the old basis and you went pre-multiplied it by the new basis that you were transitioning to, and that got this O matrix. And you did that for each of the components. There's 1, 1, there's 1, 2, 2, 1, 2, 2. And then if you multiply the vector times this operation to transpose the basis, well, you're good to go. But that's only for vectors. That could work perfectly well for our eigenvectors, couldn't it? If I wanted to transpose the eigenvectors we got right here, well, I would just, from that original basis, E1 and E2, I would just put old basis 1, E1, E1, E2, E2, and whatever new basis I wanted to come into, orthogonal basis. You know, the original basis might have been right here, right? E1, E2. Maybe I got a new basis that's some other things that I don't know what you want to call them. Give it a name, new basis. How about E1 prime? Sometimes the notation you'll see, new basis, E2 prime. It's just rotated by some amount. Okay, so I would put the new basis vectors right here, okay, and do that multiplication, and that allows me to rotate from one basis to the other. And so that works for the vectors. Here's the question now. How do you accomplish that same test for the operator? How do you do that for T? How do you do that for T? And there is a way, right? There has to be. And that's why, you know, that's how we can go from maybe momentum space to position space or to energy space, whichever one you want, by transposing basis. And again, I'm following along tutorial number 2 here. And the guy who I stole that tutorial for, he has a very elegant way of approaching this. I don't particularly like the notation, but once you understand what the notation means, it makes perfect sense. It's not exactly written this way in Griffiths. I'll show you at the end how Griffiths writes this out, but it works and it makes sense. Because we said that if I'm looking for an operator in a new basis, and I'm going to call the new basis alpha here, okay? Just,
Mr. Kowalski, are you recording this?
Am I recording? I thought I hit recording.
Yes, you are.
Okay,
Yeah.
good.
Okay.
Yeah,
There's a little recording sign in the top left.
Oh, okay.
That's good to know. Thanks. All right, I'll make that go away. Yeah, I'm coming from a new basis. I got to take the operator in the new basis, right? And I need to make this go away now. Go away. Annotate. Hit that. There we go. I have to multiply by something to relate it to my old basis, right? This is how I would find in the new basis, just exactly what we said when I started talking today. IJ, you take the new basis, pre-multiply by that as a bra, the ket is the old basis, that'll get you IJ in that new alpha basis. Go to the old basis you have, but you see what we did? We took what we said right here and we inserted, which you should recognize by now is the identity operator. We played with that a couple times on a couple of tutorials. So I inserted that thing. And of course, inserting the identity operator, which is what we talked about at the very end of the class on Wednesday, it shouldn't change the thing, but it is expressing the thing without changing it in a different basis. And then you've got 2 pieces here that you have to work with. That, come on, where's my pen? No, I don't want that. I want to go away. Yeah, that's the pen I want. Then you have 3 pieces, well, 2 new pieces to take on the original matrix in the old basis, which was the E basis. You got to multiply by those things. Now, this is where I don't like the notation. It is summed out front, but remember, anytime we said we do an inner product of vectors like this, what did we say the result was? The answer I said was a number. Yeah, not in this case though. In this case, the notation is such that since this guy and this guy are being summed on M, and it's just an implied sum on J, okay, way out here, this guy becomes a matrix. The thing in the middle was our original T matrix, okay? And then this thing right here is a matrix as well. Okay, so I'm going to define these things. I'm going to give them the names S and inverse S, because as I'll show at the end, that's what they are. We're going to call this guy right here inverse S, and this guy right here S, and they're three matrices that you multiply together to go from the operator expressed in the original basis, that E basis, the 1001 basis, into the new basis, which I'm calling alpha. And specifically in this problem, I'm going to do transformation into the basis of the eigenvectors, because I think that's an interesting result that you get from that. Okay, so we started off with T being expressed in the original basis E, and I'm going to transform it into a basis where the basis set is its own eigenvectors. Okay, any thoughts on what that might be? Kind of think, well, what's that going to look like? What's the new matrix T going to look like expressed in the coordinate system of its own eigenvectors? Basis, I guess, and coordinate system in physical space are almost synonyms, and you just have to accept that you can have multiple dimension spaces here. Okay, three matrices that must be multiplied and in the correct order, as stated right here. So let's work the problem, and then at the end, I'll show you why it works out. How's that? Okay, and so I think you do exactly the same thing we did to get the original matrix form of our operator T, our eigenvalue problem that we're using, okay? And these are the eigenvectors that we got. I'm going to stop doing this -1. That was the eigenvector associated with the eigenvalue -1. This is the one associated with +1. I'm going to call them 1 and 2 respectively, because that's what you're iterating through. It's J equals 1, J equals 2, N equals 1, N equals 2, etc. And so when you create these matrices, and again, this is why I don't particularly like the notation, you're doing this, okay? And so I'm putting the original basis right here, the 1001, and I'm putting the new basis I'm switching to right here, the eigenvectors, okay, the alphas that we found. I'm putting them right there. And so I create a matrix, a 2 by 2 matrix, by doing that operation. And so right here, if you kind of look, I go E1 times alpha 1, and I liked it in this form, but if you like multiplying those guys out, I'm fine with that too. But if you see, I pre-multiplied by E1, and I wrote alpha right here, and E1 times E2, of course, is 0, but what's E1 times E1? Well, it's 1, and I factored out the 1 over the square root of 2, the normalization constant, so that went right there. Okay, on the other hand, bring in E1 and multiply it by alpha 2, which I wrote right here. Okay, so this guy went right here, right? This guy is going to go right here. Again, pre-multiplied by E1. And again, I get a 1, E1 times E2, 0. All right, do the same thing down in the bottom, okay? Comes right there, right? Because alpha 1 is in both of those two in both of those two rows of that column, of the first column. Only now I'm pre-multiplying by E2. So what must survive is the I, because E2 times E1 is just 0. It's orthogonal. E2 times E2 is just 1. So that puts the I there. Again, brought out the 1 over the square root of 2. And then same thing over here. And I got that guy right there. So there is the matrix that I called S minus 1. There are the elements achieved that way. This is the notational thing I don't like. Every other time we've done an inner product of this sort without a sum outside the front, you just got a number out of that. If you remember the one on one of the tutorials, the number was 47, for example, right? Now we're getting a matrix. Okay, it should make sense to you that the other matrix, okay, the one without the inverse sign, was just alpha En. And so I reversed the little chart I made, the little grid I made, and I put the old basis up there, and I put the new basis over here. Okay, and I have to do the same multiplication, but I had to think about what was the bra associated with the ket as a unit vector. And it's more than just turning the symbol so it points the other way, right? don't forget it's the complex conjugate. So while alpha 1 had plus I in the E2 term, the bra will have the complex conjugate, and that makes it negative right here. As I've watched people do these problems as I was going through graduate school, that's probably one of the biggest mistakes right there, is not remembering to take the complex conjugate when you're pre-multiplying by the bra A1. Okay, so let me see that. Let's do this first term here. This becomes that guy right down right here. Okay, those sets of bras, and I multiply it by E1. Well, hopefully you can see the only thing that's going to survive is that term E1 times that E1. The fact that I made that a complex conjugate is irrelevant. I think this just becomes 1, doesn't it? And I can scratch that out because that just becomes 1. Okay, what about the second one, the one right below it, where I pre-multiply alpha 2 by this guy? And by the way, I said it becomes 1. The normalization constant will slap in at the end, right? I take alpha 2 here and multiply it by E1. Again, I should just get 1 right here, right? All right, help me out now. What happens when I take alpha 1 and I multiply it by E2? Well, E1 times E2 is 0. Take a second and think about it. It should be that minus I, right? And the last one is alpha 2 times E2. It should be the plus I right here. And so hopefully that's what I wrote right there. Sure enough, yeah, bring out the 1 over the square root of 2 because it's in each of the alphas, just like it was in each of the alphas, the eigenvectors up here. And that's my other matrix. And now to transform my original T, I'm going to put it right here. I'm going to put this thing I called S to the minus 1 right here. And I'm going to put this guy S right here. And that should follow. Go back one here. Oh, there it is. That should follow the pattern we said, where you start with the original matrix, inserting the identity matrix. So I got this guy, and inserting the identity matrix, I got this guy. These two matrices I construct have to be multiplied in that order. And I think we've stayed consistent to that. All right, so let's go ahead and do that multiplication. Let's take the original T right here. This is the thing I was calling S to the minus 1. Here's the thing I called S, and that should give me the new matrix in the basis, not of the E basis, the 1001 basis. It's instead in the expressing the operator T in its own eigenvectors basis. Okay, and so I think you got to be consistent. I did this operation first. Actually, the first thing I did is I multiplied 1 over the square root of 2 by 1 over the square root of 2 and got a half. And then I did this guy multiplied by this guy. So 0 times 1 minus, which is 0, minus 1 made that 1. 0 times 1 is 0, and then minus I times I just gave me 1. Did the same thing all the way through, did matrix multiplication, so 0 times 1 is 0, and then minus I times minus I, let's see, minus times minus is a plus, but I times I is minus 1. Check, check. And then if you do the next guy, you get I times 1 and 0 times I, so that's just I. And let's see, I times 1, 0 is also I. So that's the result of that multiplication. And then I won't bore you again. If you have trouble doing matrix multiplication because you've never done linear algebra before this type in any of your courses, good time to find out is how to do office hours. We'll practice matrix multiplication as much as you want. But then there's S, and there's the product right there. I had to multiply it out again. And interesting thing here, look what happens. I get a matrix whose diagonal, now it has no off-diagonal elements. My original matrix in the E basis looked like this. My original matrix in the E basis looked like this. I guess if I click my mouse while I'm drawing, it advances the screen. When I transform that original matrix into the basis of its own eigenvectors, I get that. I get what I would call a diagonal matrix. It only has elements on the diagonal elements, 1, 1, 2, 2, If there was a 3x3, it'd be 3, 3, 4, 4s, is however many you want. So that's our first observation, I guess. This is how we transform operators from one basis to the other. Okay, you got to create two matrices to do that, not just one like you have to do when you're transforming a vector. But if you transform an operator into an operator in the basis of its own eigenvectors, the result, and it is universal, is a diagonal matrix. A couple of other things, and these are proved in your textbook. I'm not going to prove them. It's a one-liner if you look at it. It's in the appendix. It's equation A65. The determinant of both of these operators must be the same. You've only transformed it into a different way of expressing it. It is fundamentally the same operator. It's just expressed relative to a different set of vectors. And if you check, this is the determinant here is 0 and then minus 1. So the determinant here is minus 1, right? I times minus I is 1, but you're subtracting off the thing that goes that way. And so minus 1 minus 0, the determinant of this guy is also minus 1. So I've given you one case, the A65 in Appendix A. That line shows you a more general proof of why that is true all the time. The transpose matrix has the same determinant. But the other thing that is true here is the trace, also proved in the appendix, now on line A68, a couple lines later. The trace we've never discussed, I think. It is the sum of the diagonals. The sum of the diagonals is the same for both these matrices. 0 here, you just kind of ignore the non-diagonal elements. Also 0 here, right? 1 minus 1 is 0. So transforming a matrix from one basis to the other really doesn't change how it functions. It just changes what it's relative to. All right, why this works. And this is not using the notation of the guy from Berry College whose tutorial I snelled. This is in the in the notation of Griffiths. Again, this is contained in the appendix. It is in A4. If you're looking for it, it's in that section. It's just a page, so if you want to read it, because I'm not clear on something. Remember, way back before
I just have a quick question.
Sure, go ahead, Peyton.
So everything that we just did before, so we were plugging things in still in terms of the y component of spin, right?
Yeah, this is actually a problem that applies. It's an example problem, so the fact that it is y component of spin isn't that important, but go ahead, yeah.
Okay, so I was just wondering, like, so that's not generalized for all operators. We were just going through that whole process in terms of the y component of spin.
No, I think the process we're doing will work for angular momentum when we start talking about the hydrogen atom. This same process works for that. Now, I'll be honest with you, as a matrix problem, it is most often applied in my experience to spin. Because spin's kind of a binary thing. So that nice 2x2 up down x unit vector, y unit vector is two states of the space. It works really well for spin, but in principle, this direct interpretation of quantum mechanics applies to any problem. Okay. The specific example we're doing is the y component of spin, but the fact that it's y component of spin is just something I threw in there for to kind of give relevance to the problem. It's just a math problem to some degree of, but is a very appropriate math problem for quantum mechanical systems. Okay. All right. Anyway, back to and you remember we talked about this thing. How do you do a linear transformation on bases? Okay. And I remember Jacob Stein out there. I think you're here today. You said, no, you got it wrong. It should be, he said, I got this wrong right here. Okay. He said you wanted it to be 1, 2, which is what it would be for the coefficients of the vector and the matrix. But the basis vectors themselves, the unit vectors, transform just the opposite. And I kind of intimidated him into going along with me, and we saw that it worked at the end. But we're going to be doing that same thing. Remember, we say that the basis transforms like this, and it's normally row times column. I guess it's backwards here, right? The two things you multiply together are the row and the row, which is not exactly the same as how you do elements. But the good news is, if that's how you transform basis, and I'm looking, if you notice my notation, I put the old basis, the 1001 basis, I'm still going to be calling E, and the new basis that you can express any of the old basis in is the unit vectors. Now, of course, we only had two, right? We were just playing with this portion of it. But in general, this, you can have more, right? Relating to Peyton's question, I can have some other quantum mechanical system that needs more than a 2x2 matrix. And we can, like angular momentum, which has a 3x3 matrix, for example, and we could do the same thing. But the good news about this is, if you believe it, because I intimidated you before the break and you just believe in, the coefficients do transpose the way you wanted them to. Well, that's a J and that's a J, okay? So that is still true in this method of transforming the basis between an old, and I guess I should finish up here, write the word new, the alphas, okay? Well, that's good. I guess this S right here, that is exactly the matrix that I just called S in the previous example. And so what I said, I guess, is if I want to take a vector from the old basis to a new basis, I multiply by that thing called S. Okay, and if you think about how I constructed it, it was exactly the old new system that we would do to transform a vector. Okay, so that's good. And by the way, my notation for the matrix is the double arrow, and the vector, of course, is the same arrow we've always used for a vector. I've seen that as a conventional notation. Some mathematicians put it underneath. You know, everybody has their own style on that. Our book just doesn't do anything. It just puts it in this weird font, but that's a matrix. In the problem we're doing, it's a 2x2 matrix. Okay, what if, on the other hand, I wanted to solve for the vector in the old system? Well, I just multiply by the inverse of that matrix. That brings us to a point, I guess. For our problem, S has to be a non-singular matrix. A singular matrix is one that doesn't have an inverse. So these S's that I'm talking about have to have inverses so that I can do this operation. I can find the old vector in terms of the new. Okay, for any linear transformation, we can take a set of coefficients into a new set of coefficients. I'm going to call the new set primed. And so I guess if I'm in the old basis, the 1001 basis, I take a vector, I multiply it by some linear transformation T, which is what we did, right? And I can get a set of coefficients in the new basis. I can do that anytime I want. Now let's see. The vector expressed in the old basis, I said, is just going to be that guy. So the vector expressed in the old basis, I'm going to replace with that. Okay, and we're sorted there now. What if I want to transform a basis now, a vector from the old basis to the new basis? That one that I've already put through just any linear transformation, I now want to turn that guy into a new basis. Well, I would just pre-multiply by this thing. Okay, and so here's the bottom line, I guess. In a particular system, this combination of three matrices multiplied together takes the vector from where it was before the transformation to the state you want it after the transformation. So apparently this thing right here has the same function as this guy right here in the old basis, right? Between the unprimed and the primed, unprimed at the primed, that gets replaced, okay? And that's, I guess, our point. That's my point here. This is now the transformation in the new basis, the alphas. And you do that multiplication. By the way, you may wonder why this is referred to as, these matrices are referred to as S. We're doing what's called a similarity transformation. And that's why the two matrices you use to transform the operator matrix are given the symbol S. They're non-singular, okay? I just want to give you one more piece of evidence, not formal proof, of why I'm really not changing the operator, the matrix operator, when I go from one basis to the other. S and S inverse, well, they really are inverse. When I worked through creating them, I didn't take an inverse per se, but once I've got them, if I multiply them together, well, what should happen when I multiply the two matrices involved in a similarity transform together? I should get the identity matrix, right? That should prove that I haven't really changed the matrix. And sure enough, if I take the S and the S to the -1 and multiply them together, just check a couple terms if you want. 1 times 1 gets me 1, and then minus I times I gets me 1. So 1 plus 1 is 2. But this next element right here, that goes 1 times 1, which is 1, and then plus minus I times minus I, which is -1, and that gets me 0. And I'll get the same thing over here. And of course, the 1 over the square root of 2 gives me a factor of 1/2, which creates the identity matrix. So in terms of changing, I guess, magnitude, if you will, of the transformation, this does nothing. Okay, absolutely doesn't do anything. This is the way Griffith expresses it in his work, but you can see it is equivalent mathematically to what Professor Timberlake down at Berry College, whose tutorial I stole, he inserted an identity matrix as well. He just did it as that bra-ket pointing together piece. I guess it's a ket bra as an identity matrix, but that's what these S's and S primes do. Okay, I think that's all I have to say. Hopefully, you see the process that you have to go through in order to solve the tutorial, which Jacob asked about, which is posted up on Canvas now and due next Wednesday. I do want to warn you, it's 4 pages, and he has you transfer or transpose, I guess is the right word, your matrix operator into 2 different bases. One into the basis of its own eigenvector, and then he has you create a new set of eigenvectors and transform your original matrix into that, and then just check it to make sure things are working. So going through this a couple times is a little tedious, takes more than just a few minutes to run through it. Because remember, now you're doing matrix, you have to get 4 operations just to multiply something. And then you have to have 2 matrices to transform a matrix. So it is a little long in the tooth to do. That's why I made it due next Wednesday instead of Monday. And that's all I got. Any questions for anybody? All right, it's a mathematical process when you're working the next tutorial, which I suspect most people today are finishing up the one that's due today, okay? Any questions on that? Now's the time as well. Otherwise, I'll close this out. I can certainly stop recording at this point, and I'll close this out. And if people want to hang around, nope, discard the annotation. We can either work some problems, or I can pick up with office hours later on this afternoon. I'm probably going to go with 3:30 is the time again, because I have a webinar to go to.
So A is representative of any vector. Is that what we're saying here?
Just A or alpha? Or are you talking about the tutorial?
No, I'm talking about this last slide you're on.
Last slide I'm on.
Where it says experience, or like for any linear transformation.
Yeah. Okay. Yeah. So isn't this how I transform coefficients in a, so A is any vector. Absolutely. It'd be like A1, A2, A3 in a particular basis. I can just transform it. And that's how, right? That's how it transforms.
Mm-hmm. So this can also be expressed in terms of Dirac notation, right?
Yes, I think I could, right? How would I write it as a Dirac? Let me go back and get my pen here.
It would just be a primed Dirac notation, basically. Is what I'm understanding.
Here's what I think I would do here. Let's see. I can get that pen up, I guess. That text. Yeah, I'm not any good on this thing anymore. So let's go back to this. Way I would write this in Dirac notation, I think I would write. Okay, I gotta get my pen. Let's see. This would be alpha in maybe an E basis, and then I would be saying S, and this would be alpha in the alpha basis. And maybe that was probably clunky notation. Maybe I should have just made this capital A and made this capital A. So capital A is a set of coefficients, A1, A2, A3, dot, 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 right? And so that's what I'm calling this, but in one basis, and then there's A in the other basis, and I'm multiplying it by this thing S. That's the way any linear transformation would have worked if I had just put T. This is a particular transformation that goes from one basis to the other. Is that okay on your Dirac notation? I think that was your question. How would I write that in Dirac notation? I think we would have written it like that.
Okay.
Yeah, and if it was just any old transformation, not necessarily one that does a rotation or something like that, I would have just called it T. This is a particular one that transforms between this basis and that basis, that being the alpha basis up there. All right?
Okay, so there's nothing you need to do special to differentiate between just any arbitrary vectors and bases?
Yeah, and that's why I picked this fact that I was doing this on a vector, just so that at the end I can show, hey, this is a transformation between that vector, maybe rotated in space with T, and that was in one basis. If I go back to the original basis, I need to do all three of these things in order to create the guy that does that transformation. That was the only reason I even introduced a vector at all. Because what we're talking about here still is how do I transform this T, this thing that was the key element of my eigenvector equation, right? So T as an operator, or T as a matrix now, using this notation, operating on some eigenvector, gave me an eigenvalue times that eigenvector back. Well, originally we were expressing this in that basis E, and then we transposed it over to expressing this operator in terms of the eigenvectors themselves as a basis. So essentially we've lined the eigenvectors up with the coordinate axis, right? A clever thing to do. Initially, we've got an I and a j, and the eigenvectors are two other vectors that both have components in the I and the j direction. By doing this transformation, we line the eigenvalues up with the new coordinate system that we're in. Does that make sense?
Okay, yeah, that makes sense.
Yeah. And I guess if I had probably a way to draw that, there's your original E1, and there's your original E2, and we had the eigenvector E1 and the eigenvector E2. And what we've done is we've rotated the basis so that the eigenvectors are the basis set. But the question then is, okay, well, what do you have to do to the transformation that caused the creation of those eigenvectors in order to do that transformation? We're still back to how do you transform the operator? And that would cause the two to line up. And that's supposed to be alpha right there, isn't it? That's alpha 2.
Okay, so essentially what we're doing is just an easier version of that thing we did before with the Gram-Schmidt procedure, basically.
Gram-Schmidt was a procedure you used if your basis was not already orthogonal. Gram-Schmidt took a non-orthogonal basis and created an orthogonal basis. In this case, I started with an orthogonal basis, and I transformed to a set of eigenvectors. Eigenvectors were orthogonal themselves. If I guess I had a degeneracy in my eigenvalues, go back right here, my eigenvalues were unique, plus and minus 1, right?
Oh, okay.
Right. If the eigenvalue had turned out to be plus 1 plus 1, or plus I or something like that, then I would have had to go through the Gram-Schmidt procedure in order to turn them into an orthogonal set. Okay, and then I could have transformed the base to that eigenvalue set and expressed the operator that created that degenerate eigenvalue. I could have created a transform matrix that would be in that basis. Does that help?
Yeah.
Two different things now. What I'm more referring to, back we talked about when we just rotated a vector, we use this procedure, a single, we called it an O transformation on that one tutorial we did, just rotated a vector. Just needed one matrix to do that. To transform the operator, a matrix, you need two vectors. You need 2 matrices to transform a matrix, whereas to transform a vector, you only needed 1 matrix. And that kind of should make sense from matrix theory. What do you get when you multiply a matrix times a vector? You get another vector.
Mhm.
If I
Yeah, that
want,
makes sense.
yeah, I need 3 things to multiply together to create a new matrix. All right.
Awesome.
Yeah, and I think it's one of those things. You can listen to my words, but I think what you all have to do is sit down, work that tutorial by yourself. You'll find it to be similar to the ones I did, maybe even a little easier mathematically, because the operator you're going to start with won't have any complex numbers in it, no i's. It'll just be ones and zeros. But go through that process of creating the eigenvalues, finding the eigenvalues, finding the eigenvectors, and then transforming the original matrix into the basis of its own eigenvectors and see what you get. You should get a diagonalized matrix. You should determine that it's exactly what you expect, because the determinant of the original matrix and the transform matrix are the same. You should find that the traces are equal, and then if you work through that process once yourself, it should make more sense. All right, now class is almost over. I guess we got about 2 more minutes. I will be around at 3:30. I'll set up another Zoom room for any help on the previous tutorial. If you get started on this one, you got any questions, you want to check make sure your transformation matrix is correct in step 1, I guess, before you go work the remaining 4 pages, because that would be bad if your original T matrix is wrong. That would be a lot of wasted work. You'd have to come back and restart everything, but we can talk then. All right. I'm going to stop sharing here. I'm going to stop the meeting and the recording.